Hello and welcome everyone. My name is Dane Menke. I am the Digital Marketing Manager here at REGENESIS and Land Science. Before we get started, I have just a few administrative items to cover. Since we're trying to keep this under an hour, today's presentation will be conducted with the audience audio settings on mute. This will minimize unwanted background noise from the large number of participants joining us today. If the webinar or audio quality degrades, please disconnect and repeat the original login steps to rejoin the webcast. If you have a question, we encourage you to ask it using the question feature located on the webinar panel. We'll collect your questions and do our best to answer them at the end of the presentation. If we don't address your question within the time permitting, we'll make an effort to follow up with you after the webinar. We are recording this webinar, and a link to the recording will be emailed to you once it is available. In order to continue to sponsor events that are of value and worthy of your time, we will be sending out a brief survey following the webinar to get your feedback. Today's presentation will focus on proven methods for saving time and money using in-situ activated carbon remediation. With that, I'd like to introduce our presenters for today. We are pleased to have with us Matt Burns, Technical Director of Environmental Services at WSP. Matt has more than 25 years of professional chemistry and engineering experience. He is based in Boston and is responsible for the technical depth and breadth of the contaminated land site investigation and remediation service line. Matt also brings chemical and microbial process expertise to assist WSP teams with challenging investigation and remediation projects in the US and across the globe. His area of expertise includes practical application of microbial and chemistry-based innovative remediation. We're also pleased to have with us today Maureen Dooley, Director of Strategic Projects at REGENESIS. Maureen has more than 25 years of experience in the remediation industry. In her current role at REGENESIS, she provides technical leadership for complex soil and groundwater remediation projects throughout North America, as well as remediation design, strategy, and business development in the northeastern United States and eastern Canada. All right, that concludes our introduction. So now I will hand things over to Maureen to get us started.
Well, thank you, Dane, and welcome, everyone. I understand how busy people are, so appreciate you choosing to participate in the webinar presentation today. The title of today's presentation is Proven Methods for Saving Time and Money Using In-Situ Activated Carbon. We're very pleased to have Matt Burns with us today to make this presentation. I've had the pleasure of working with Matt for many years, and when it comes to site remediation, I appreciate his ability, where he has an academic level of understanding of complex aspects of remediation, yet applies this knowledge in a practical way that results in effective application of technologies that achieves the goal of obtaining a reduced cost to closure. So Matt, why don't you introduce today's talk and let everyone know what we'll be covering?
Sure. Thank you, Maureen, and welcome everyone. As Maureen and Dane mentioned, I'm with WSP, and I'm fortunate to work with a great group of colleagues and some truly phenomenal clients. They've supported our science-based approach that validates remedies in a fail small, succeed big manner. Together, along with reputable and knowledgeable remediation professionals like Maureen and the others, our colleagues at REGENESIS, we've been able to close out a lot of sites together. If you would like to contact either Maureen or me, our email addresses are provided here, and they'll also be provided in the last slide if you don't have time to jot them down now. LinkedIn is also a great way to contact me. So hopefully everyone is healthy and physically and mentally and being safe. And I guess there's some good news starting to trickle in with vaccines and therapeutics, and hopefully we turn the corner on this thing and get back to normal interactions soon. Until then, please check in with more isolated friends and family and neighbors. Actually, I have one ask of all of you. It's my first ask of any webinar, is that pick one person in your life that might be a little bit more isolated because of COVID and give them a call tonight. All right, let's get to the webinar. So during this webinar, we're going to cover ideal characteristics of in-situ amendments. We're going to take a look at life cycle costs of remediation using and in-situ remediation using these amendments, or versus pump and treat. And we'll go over a couple methods of how to do apples to apples mass removal comparisons between pump and treat and those in situ alternatives. Even in the presence of some confounding conditions, such as use of activated carbon and beta elimination stimulating amendments, these apple-to-apple mass removal comparisons can be made, and we'll go over those. With that, I'll pass the baton off to Maureen.
Well, thanks, Matt. And honestly, related to the COVID, I just think that's a great suggestion to reach out to people. So thanks for that. So I want to briefly describe the reagents that are used in the case studies that'll be presented. And the focus here really is on the colloidal reagents. So first we have plume stop. So plume stop is a colloidal activated carbon that's a sorbent designed to remove contaminants from groundwater and promote degradation. The plume stop is composed of fine particles of activated carbon that are suspended using a unique polymer. The plume stop behaves like a colloid, binds to the aquifer matrix, and rapidly sorbs contaminants and expedites contaminant degradation. I mean, a real key feature of the carbon is the vast surface area. It's something like, 100 acres for 1 pound of the activated carbon or colloidal activated carbon. And what that translates to is rapid sorption and also provides a vast surface area for microbial colonization. And another important factor is that we can inject the colloidal activated carbon under low pressure and get widespread distribution. Another reagent that can be used to enhance remediation efficiencies is sulfidated zero-valent iron. The SMZVI is also a colloidal reagent at 1 to 4 micron in size. So why is sulfidation important? Well, when you have bare ZVI in an aqueous solution, it's going to react with water, and that's what's favored. So while generating hydrogen, that can support biological degradation, but is also a wasted reaction. So if we amend the iron by depositing a layer of iron sulfide, you can increase the efficiency of the zero-valent iron. In some of our internal studies, we've been able to see a 30 times increase in degradation rates when using sulfidated ZVI. And the other important feature is we're going to reduce daughter product formation with chlorinated solvents. Now, is it going to be gone completely? Probably not, but certainly you're going to increase your conversion and your rate of conversion to ethene and ethane. The other characteristic of the SMZVI is that it's colloidal, and it's a small particle, and as I said, can be injected easily. So you see in this picture, you have the SMZVI on the left, and so that's a suspension. And so again, as I say, you can inject this easily, but the larger particles are going to tend to settle, as you see with a 40 micron ZVI in water. And to be able to inject it, you may need a thickener like a guar, and you're going to have to use high pressure or fracturing. So with both of these colloidal reagents, and in this figure, what we're going to see is an illustration of the colloidal reagents being injected into the subsurface. And as mentioned, it's injected under low pressure. And our ability to distribute the reagents across the target zones is critical to the success of any project. This is a key advancement. So think of these original permeable reactive barriers where you needed to create trenches and physically mix in iron to create this iron wall. Now we're able to cost effectively apply and inject using methods like direct push, where ultimately we're going to paint the subsurface at these targeted zones with iron and carbon to be able to create something like a PRB. So in this slide, we're looking at, we refer to our mode of action. So initially, you have the colloidal carbon becomes attached to the soil. And so as the contamination moves through, it's going to sorb. And so we also typically co-apply an electron donor or electron acceptors to promote biodegradation. And we may also include an ISCA reagent like SMZVI. And so these reagents are set up to create conditions to enhance degradation. But in addition, you're going to be able to manage back diffusion. So while we have this sorption and degradation that continues, and the sorption sites are freed up in the barrier and it's maintained over the long term. But we're also able to manage that contamination that may be migrating from finer grain materials into the more productive areas or more conductive zones. So in essence, we're not going to see rebound because we're able to manage the back diffusion. So this allows us to achieve and maintain low cleanup standards, which also can mean, meeting part per trillion levels with PFAS. There may be no degradation with a PFAS compound, but we're still able to meet sometimes these very low cleanup standards. So some of the key features of utilizing these colloidal materials is, one, they last a long time. It could be years to decades is the sort of treatment time we can be looking at. We can work with a wide range of contaminants, VOCs, petroleum hydrocarbons, chlorinated benzenes, PFAs, and our results can be very fast. And something else I want to emphasize is an ability to be predictable. We can use models, and we're using isotherms and degradation rates, and allows a level of predictability. These are environmentally friendly. If you're looking at sustainable sort of applications, this certainly fits the bill. Flexible, we can combine with different technologies, and then ultimately it gives us an ability to reduce liability and save money. So with that, we'll turn it back over to you, Matt.
Thanks, Maureen. Well, last year, WSP and REGENESIS collaborated on this ebook. It's real world business cases where in-situ remediation saved time and money versus pump and treat. There are 3 case studies presented in there. In each case study, there was a brief site background and technical discussion. But the primary focus was on life cycle cost comparisons between in-situ technologies and pump and treat. 2 of the featured sites included in-situ remedies with plume stop-based treatment. The other was in-situ chemical oxidation. You can download the ebook from the REGENESIS website. You'll find ebooks under the resource tab. While you're there, I also recommend that you explore the content. There's a lot of good information in that tab. So case study 2 is one of the featured in the plume stop application sites inside the ebook. I'm singling it out because I've presented on this site as part of 2 other REGENESIS webinars, and it would be a chance for some continuity for those who attended the previous webinars. There's a lot of technical content in those previous webinars that take really deep dives into advanced diagnostics and the science behind site characterization and the selected remedies. I'm not going to talk about that stuff today. I'm not taking that same deep dive. Today, we'll focus in on addressing the value of in-situ remediation as compared to pump and treat. Here's a refresher on the Arkansas site background. From the information written on the logbook, you'll see that we performed 2 pilot tests at this site before going full scale. In 2016, we applied amendments to stimulate biogeochemical reduction through biogenic formation of iron sulfides from native and introduced iron and introduced sulfate. The amendment formulation also included nutrients and a bioaugment to stimulate biodegradation along the hydrogenolysis pathway, sequential reduction pathway. I've found that bioremediation is very compatible and synergistic with abiotic reduction. A more in-depth discussion of that treatment is in the May 2018 webinar that you can access through the resources tab on the REGENESIS website. And in 2017, a plume stop-based pilot test was performed. More information on that pilot in the technical deep dive was presented in the May 2019 REGENESIS webinar. So anyhow, the site is a former manufacturing facility that began operating in the early 60s. Operations included the use of chlorinated solvents. Contaminants include TCE and its daughter products over a wide area. The affected groundwater is present in fractured sandstone. A teleview image of the matrix is shown on the right side of the logbook. This sandstone has a relatively high primary porosity, as well as a significant fracture network. The fracture network is predominantly horizontal fracture pattern with some high angle fractures that are also present. Because of these site characteristics, we expect long-term back diffusion from this matrix. The long-term back diffusion potential was the primary driver for pilot testing, biogeochemical, and plume stop-based amendments. Both of these technologies have extended in situ longevity. Here's a plan view of the site. There's not really much to focus on this slide yet, other than to show that the biogeochemical and the plume stop pilot tests were performed in adjacent areas. And maybe this might jog your memory a bit about these previous webinars. I forget the names of sites and locations a lot, but I never forget a plume map, and I think a lot of people like that. So, all right, this is the cross section. It's probably more relevant. It shows the site conceptual model with the former facility at the top of the hill. The pilot test area is a few hundred feet down gradient of the facility. The plume discharges some VOCs to a gaining stream located about 1,000+ feet away from the facility. The vadozone sources have been excavated and removed, and a vapor mitigation system has been installed in the buildings that overlie the plume. So let's get back to the ebook and the life cycle cost comparisons between pump and treat and in-situ treatment. You can see in the left-hand column the cost comparison table. We included pilot test costs in this comparisons table. Those were $75,000 for the pump testing that we did there, and $125,000 for the in-situ pilot testing. Other design components that were included were design and installation, O&M, and monitoring. For the plume stop, for the pump and treat scenario, costs included $500,000 for design and installation, $300,000 for O&M, and about $35K a year for monitoring. The 1 year total is about $900,000 for year one. That's capital costs, largely taking up the most of that money. The costs for O&M and monitoring were extended out over a 10-year period of time. This results in a total net present value cost of about $3.4 million, and we discounted this at a rate of 3%. For the in-situ scenario, the costs include $125,000 for the pilot, $1 million for the design and installation of the plume stop in-situ remedy, and that same $35,000 again for annual monitoring. We were conservative with the in-situ remediation post year one design and O&M costs. We carried the need to reapply a fermentable substrate to keep bioremediation active and the microbes degrading the chlorinated ethenes happy. So that was was carried through every other year at $100,000 per application. With $30,000 on top of that every year for refining designs and making sure that we get that application correct every time we do it. It's also important to consider that the maintenance of the microbial community is very important in a plume stop remedy. Anyhow, the total net present value costs for the in-situ plume stop remedy is just over $2 million. A savings of about $1.4 million compared to the pump and treat option over that 10-year lifespan. The graph of the cost, shows the data in a more succinct manner. Despite the cost being about $200,000 greater, those capital costs being $200,000 greater, for in situ than pump and treat, the initial higher costs had a very quick return on investment. The high O&M costs associated with the pump and treat really make in situ a much better financial option. So, Maureen, I think you're going to pick it up and summarize a little bit of these benefits of these pump and treat systems. I mean, sorry, the in situ systems.
Yeah, no, I always like to go back to this this slide, which is really our 4 pillars of in situ remediation and some of the different components we want to incorporate, reactivity, ease of use, distribution, and persistence. But, really focusing here on reactivity. Now that the data are coming in and this project has been installed, how do you really now take a look and do this comparison? And one of the things when Matt and I were reviewing some of this data is, a question we asked ourselves. We looked at you look at degradation, you look at reductions, but really what's the total mass reduction? So if we move ahead, we install these colloidal reagents, we do all the things, but at the end of the day, what's their performance and what sort of total mass reduction has been observed? So I think Matt's going to get into some details on that and some interesting information.
Yeah, Maureen, I agree. A side-by-side mass removal comparison between in situ remedies and pump and treat would be important. After all, what good is lower cost if effectiveness isn't comparable? With most technologies, a mass removal assessment, isn't even aligned with remediation goals, right? Decreases in the concentration of regulated chemicals with treatment. So basically, what's the difference in the groundwater contaminant concentrations in samples collected at baseline and those collected after treatment? But with activated carbon-based remedies, where by design, VOCs are removed from the dissolve phase nearly immediately, discerning between sorption and destruction is really critical for making the mass removal assessment. And frankly, I think it's the biggest question I get from regulators when including activated carbon in amendment formulation. So here's a more visual explanation of the sorption mechanism. We'll take a deep dive in how to figure out these mass removal rates. So, all right, so here's a bit of an explanation of how the activated carbon works. So here's a glass of water. That's going to be our aquifer. Let's install a well. And should have added the sand first, but no, that's better. Add the contaminant, and conveniently, our contaminant is colored red. And treat with plume stop, add the plume stop, and biostimulants. You can wait a while for the plume stop to settle out of solution, as Maureen mentioned above, but it'll associate itself with the soil phase. This could take a month or two. It depends upon the groundwater chemistry of the site. Or a cationic parking agent can be added to cancel out the negative charge of the plume stop. And it would speed things up significantly. And is particularly useful for applications where limiting plume stop migration is desired, like near a water body. So you can control the distribution of plume stop. It won't run forever. You can make it fall out of solution very quickly, or wait the month or two if you want that increase in distribution from natural flow. Whether with time or with a cation application, you end up with an aqueous phase free or nearly free of contaminants by design. This is because the contaminant partitioned to the soil phase, the plume stop, which fell out of solution and becomes part of the saturated soils matrix. Hopefully it's degrading too. Why is this important? Why is degradation important on that activated carbon? Well, following the treatment with activated carbon, the groundwater concentration, the aqueous phase concentration, is like an order of magnitude lower than in pre-treatment concentrations. It often complies with regulatory standards, but that's not a good comparative endpoint sorption does not destroy contaminant mass. Simply looking at changes in groundwater VOC concentrations just isn't appropriate. It can even be detrimental to do so. That's because activated carbon has a limited absorptive capacity. Room needs to be made by destructive treatment to accommodate additional contaminant loading. The additional loading can come from, for example, migration of upgrading contaminated groundwater into the treatment zone, like in a hydraulic barrier configuration or in a barrier configuration, or by back diffusion, as Maureen mentioned in her illustration. It can even come from naturally occurring organic materials. Without contaminate destruction, additional contaminant or naturally occurring organics may eventually exceed the sorptive capacity of the activated carbon and potentially bump off contaminant. Here is an older but applicable guidance on granular activated carbon. On the second page, it notes there are high levels of background organic matter may result in rapid exhaustion of carbon. It's pretty easy to imagine a scenario where background levels of organic matter, even lower than that 10 milligram per liter amount noted in the guidance document here. When continuously loaded, this amount of organic matter background could cause an issue, potentially leading to desorption of target contaminants into the future. So it's important to have a destructive mechanism included to make sure the remediation is complete and that there are no surprises in a couple of years down the road. And of course, complete degradation is the ultimate endpoint to assess the effectiveness of any destructive remediation technology. In the May 2018 REGENESIS webinar, we took a really deep dive into diagnostics to demonstrate degradation of sorbed contaminants. The webinar compared degradation pathways to taking a trip to an unfamiliar area before GPS. Back then, after every turn, I would look for visual clues, landscape features, and signs that indicate that I'm on the right road. Observing these clues, the diagnostics used along the trip to my destination, right? If I look at these signs and key points, then the consequences of making a wrong turn would never be that significant. But if I didn't look for these signs and landscape features very frequently and miss something, then I could end up way off course and maybe not even reach my destination. The degradation pathway, or pathways in the case of combined remedies, is the remediation roadmap. The specific reactants, products, intermediates, nutrients, catalysts, etc., and all these end up in this equation. And they all vary, of course, by the contaminant being treated and the pathways that you're trying to stimulate. Key reactants and products, anything needed to facilitate the reaction, are great candidates to include in performance monitoring plans. But the performance monitoring plans don't need to mirror deep dives into that you do for M&A type investigations. For M&A investigations, the degradation pathway is unknown and needs to be identified, and the stoichiometry of the equation needs to be known. The presence of enough reactants, the proper conditions to drive and complete the degradation, all needs to be figured out. At bioremediation sites, the design engineer selects the pathway to stimulate and provides the proper conditions. Careful consideration is given to the amount of reactants, the macronutrients, electron acceptors, donors, everything that's needed to drive the reaction. So performance monitoring is really, with engineered system, is destination verification at the working level. Are there any issues that need to be fixed level of engineering and performance monitoring? So observing expected trends is evidence of activity along the targeted degradation pathway and realizing design goals. The webinar in 2018 and 19 went into detail on assessing the entire degradation pathways, looking at direct evidence and mechanistic data and even empirical relationship data. For assessing mass removal, though, if that's what we're focusing on, you can just look at the direct evidence of degradation. Contaminate concentrations decrease and end product accumulation. Isotopic data can also be used to estimate mass removal, but I don't typically use isotopic data that way. I use it more qualitatively. It answers a simple question: is it degrading or not? I don't typically try to correlate, appropriate enrichment studies to field conditions and tease out mass removal, but that can be done. As I'll be showing in the examples today, there are a couple of ways to get around some sorb mass issues and using really simple methods and not having to rely upon some of the more advanced diagnostics. But first, Maureen's going to tee up the discussion with a case study.
Oh, thanks, Matt. So, this question, do we have biodegradation? We're dealing with a colloidal carbon, it's sorbed, and we consistently get this, how do I know things are degrading? So I just want to give an example here, and also just refer back, we have a lot of proof of concept lab studies that have been conducted looking at this question, and you can go to our tech bulletins on our website, but I wanted to get into this direct evidence. So here's an example of a barrier that was installed where we have plume stop, SMZVI. We also have HRC to promote reductive dechlorination along with some microbes. We have a well within the barrier area, and then there's wells that are down gradient of the barrier. Next slide, please. So in the results, what we see is a very rapid reduction of the PCE and TCE. Now that's something we certainly would expect with the colloidal activated carbon, but we very immediately saw an increase in formation of ethene and ethane. So this is really the ultimate, direct evidence that you would be able to obtain and show that you're getting degradation. And interestingly enough, we had really no cis or vinyl chloride that was generated. And again, this is the well that's within the barrier itself. So next slide, please. So in the down gradient wells, what we see is, over time, we're starting to see the reductions of the target compounds. The red line refers to TCE, but the dotted line that you see there is the concentration of TCE that we predicted over time, since we incorporate internal models that allow us to design and determine how much material we'll need to be able to achieve a certain, barrier longevity. So we see the TCE degradation is actually doing better than the predictive model. And then the yellow and sort of orange yellow color represent the cis DCE and vinyl chloride that's present down gradient. And you're seeing that reduction. And compared to our predictions, the cis DCE is actually doing a little bit better, and then the vinyl chloride. But this is really just to, again, illustrate that you can install the barrier, you can get ethene, ethane formation, which gives you direct evidence of degradation, but also we do have a level of predictability here, so we can look and see, is everything performing as expected? So with that, Matt, we'll turn it back to you.
Thanks, Maureen. So now that we know, Maureen just showed a great example of showing that degradation is happening, and you can't argue that degradation is not going on in the presence of ethane and ethene in that system, but it doesn't do a complete mass balance so that you can know how much has been destroyed. So that's what we're going to focus on for the balance of this talk. So let's get back to this Arkansas site. So we went beyond the pilot test, and we performed a full-scale plume stop plus bioremediation treatment in April of 2019. Unlike the case study that Maureen just presented, ZVI was not included in the formulation. We injected through 26 PVC wells, shown in purple on the map to the right. In total, nearly 200,000 gallons of amendment and mixed water were injected. an average flow rate of about 12 GPM per well. We got through the injections relatively quickly by using a manifold to simultaneously inject up to 4 wells at a time. There were really no surprises during application. The application was really consistent with the design parameters identified during the pilot testing. And we also had some great crews out there performing the work. So the goal of the remediation was to limit the transport and promote of the VOCs and promote biodegradation. Here's a very simple degradation pathway for TCE, the contaminant concern at the Arkansas site. It's our roadmap, and I'm sure you've all seen this before. There is no mention of the dihalococoides, pH constraints, cobalamin lower ligand requirements, et cetera, in this simplified roadmap. Those milestones are included in those other webinars. But it is detailed enough to depict what happens to aqueous phase concentrations of TCE and its hydrogenolysis degradation products. When you end up treating these with activated base carbon amendments. TCE has a great activated carbon isotherm. It sorbs to the activated carbon, which is associated with the solid phase, as Maureen has discussed, and is removed from the groundwater. So groundwater samples won't have any or not much TCE in it. DCE has an okay isotherm. Some of it will sorb and some will remain in groundwater. Vinyl chloride has a poor isotherm. Typically not much of it is sorbs, and most of it is in the groundwater. Ethene doesn't partition appreciably to the activated carbon. Just about all of it remains in the groundwater. Because ethene is the desired end product, it doesn't sorb to the and because it doesn't sorb to the activated carbon, and it's fairly conservative, and by it's can be used as a good indicator of mass destruction. And by being conservative, what I mean there is that it doesn't really degrade in anaerobic conditions that are established as part of the conditions needed to stimulate the sequential reduction. So ethene concentrations increase in groundwater samples with time and treatment, and that increase can be used to quantitatively estimate mass removal along hydrogenolysis pathway. But ethane will degrade anaerobically, and since there's always some oxygen leaking its way into an open system like at a remediation site, it leaks in from like air-water partitioning and stormwater infiltration. An ethene-based mass removal estimate, if anything, is probably biased a little bit low. There's probably more generated than you're actually quantifying, because oxygen aerobic processes, even though they're not very, very active, there's still a little bit gotten in there, will lower the concentration of ethenes compared to what you're measuring. But there's no harm in being a little bit conservative. So here are the results. The Batesville site. After the average ethene concentration from all site wells measured in the year 1 post-treatment groundwater samples was about 190 micrograms per liter, or 6.8 micromolar. Extrapolated across the entire groundwater volume, the entire plume, after 1 year, that's about 1,700 moles of ethene were produced. This is equivalent to about 500 pounds of TCE that was destroyed by the treatment. This is pretty good when considering the sequential nature of the degradation pathway. It takes time to progress to the phase when ethene is the most abundant data product being produced along the degradation pathway. For the pump and treat comparison, a hydraulic barrier got some serious consideration for implementation at the Arkansas site. We collected the data needed to design it, including a substantial pump testing activities, where we were able to gather key design criteria and quantify those for design purposes. In part, some of those criteria were, we identified a sustainable yield about 2 GPM across the site, and we identified a 130-foot wide drawdown perpendicular to the groundwater flow. The drawdown was of at least 2 feet. So 2 feet drawdown across 130-foot wide cross-sectional area. It's pretty substantial. So based on this data, a network of 10 extraction wells with a cumulative extraction rate of about 20 GPM was contemplated. To calculate the expected mass removal rate over the first year of treatment, the same period of comparison as the plume stop bioremediation scenario we just discussed, baseline pre-treatment groundwater chlorinated VOC concentration data were used. The average chlorinated VOC concentration was about 5,500 micrograms per liter, or 47 micromolar. Over 1 year of treatment at 20 GPM, with you using an uptime estimate of about 75%, 1,400 moles of CVOCs, or the equivalent of 410 pounds of TC, would have been removed by that hypothetical pump and treat system. So here's the year 1 mass removal comparison. Equivalent of about 500 pounds of TCE removed for the in-situ remediation versus 410 pounds for the pump and treat. Basically the same or close enough. So equivalent mass removals between the technologies. But, before I ran these calculations, I thought for sure that pump and treat would outperform in-situ during the first year. This is because the sequential nature of the degradation, the time microbes take to reduce TC to DCE and DCE to vinyl chloride, before getting to the serious ethene production phase of the sequence. So, okay, in summary, at this site, mass removal performances were similar, but the costs were not. The in-situ option saves about $1.5 million over 10 years as compared to the pump and treat alternative. Our decision to implement a in-situ remedy at the Arkansas site over a pump and treat remedy is looking pretty good at this point, and that we're going to be able to realize those savings with at least a comparable performance between the in-situ treatment and the pump and treat. So the value is there for the in-situ remedy. So on to another site. I like to add iron, and Maureen does too, as she showed in her presentation. I like to add it as either ZVI or as biogenic ferrous sulfide, like the pilot test we completed initially at that Arkansas site. Both of these stimulate the elimination pathway, where the ZVI or iron sulfides, they both stimulate that elimination pathway, or beta elimination is what you probably commonly hear. Lots of technical reasons that I've spoken out at length during some of these previous webinars for combining bio. They're very complementary pathways. And I've found that with these pathways, 1 + 1 equals more than 2. But quantifying RAS removal becomes a bit more difficult with these amendments. With TCE being sorbed to the activated carbon, that's a confounding factor, but also this poor product recovery is associated with using these elimination stimulating pathways. But there is a relatively easy way to calculate mass removal with activated carbon plus biostimulation plus beta elimination pathway stimulation. Perform a saturated soil balance, mass balance with time. That's a great way of figuring it out. So figuring out direct comparisons of how much contaminant has been destroyed. Don't just look at the aqueous phase, look at the saturated soil phase. It's the CVOCs in groundwater plus the CVOCs in soil. What happens with those with time? To do this, in addition to collecting groundwater samples, saturated soil samples will also need to be collected. The soil data will need to be adjusted by subtracting out the amount of VOCs attributable to the aqueous phase, the VOCs that are in the groundwater. Determining the CVOC contribution to soil moisture is done simply by multiplying the percent moisture of the saturated soil by the groundwater results, then just from an adjacent well, and then just pull it out of there. After the adjustment for soil, an adjustment for soil bulk density needs to be made too. I like to keep it simple and multiply by the dry bulk density of a cubic meter of soil, about 1,600 kilograms. With the soil VOC content defined, all that's left is back in groundwater. So what's the concentration? How much groundwater VOC contribution needs to be put into that the unit volume of aquifer material? And in the case, my examples, I like to use the cubic meter again. The groundwater contribution of the CVOCs is simply multiplying the CVOC concentrations by the soil porosity and whatever volume that you use. Again, I like 1 cubic meter. So, for example, for porosity of 30%, multiply the concentration that you get from the groundwater data times 300 liters. With the VOC concentration normalized and the mass of CVOCs per unit of saturated soils. So we've mathematically just adjusted everything. So we're not just looking at the soil concentration, and we're not just looking at the aqueous concentration. We're looking at the concentration of CVOCs per unit of saturated soils. Because you're looking at it as a per unit of saturated soils, a direct comparison of the disappearance of CVOCs with time can be made. I know a geoprobe's in this photo, and I know it's rigged up for injections and not for soil sample collection, but it's a great photo. In any way, I don't use geoprobes or any other type of drill rig to collect those saturated soil samples that are necessary for this sort of analysis. What I do is I use aquifer material in situ microcosms. The matrix for the in situ microcosms are collected during an earlier investigation phase or even during injection well installation. The samples are dried out to remove VOCs. And for bedrock, the rock is smashed up and sieved. Dried samples are then loaded into screen housings, and several ISM units, those screen housings, are suspended within each monitoring well for at least a couple weeks before a treatment is performed. This is done so that the CVOC groundwater soil equilibrium has time to reestablish. And with soluble amendments, in hydrocolloids like plume stop and S-micro-ZVI, the ISM is treated in situ with the rest of the aquifer, so in the same exact manner. The ISM soil samples can then be retrieved with groundwater from that same well to perform the saturated soil matrix mass balance. There are some other data like the ability to quantify plume stop delivery efficiency that can also be teased out of these aquifer material ISM data, but I went over that one in the other webinar as well. So if you're interested in that, please check it out. So after one of my REGENESIS webinars, a new client asked to take a look at one of their underperforming sites. The site had a very expensive and inefficient property line hydraulic barrier pump and treat system. Well, we looked at it, and the pump and treat system had some big issues. So we performed pre-designed studies in that fail small, succeed big science-based manner that I mentioned at the beginning of the webinar. And these studies included hydrophysical investigation that identified some flow zones, or the high mass flow zones, and in situ microcosm study that's different than what I've been just talking about. It's the microbial insights in situ microcosm studies, which you amend a small sample, those in situ microcosms, and take a look at all those advanced diagnostics to nail down an amendment formulation. So we were able to demonstrate on the small scale the viability of the in situ remedy before we scaled it up to full scale or even pilot scale. So it's another one of those great fail small, succeed big methodologies. Anyhow, in July 2019, we decommissioned the pump and treat system and performed the in situ treatment. The amendment formulation included plume stop, biostimulants, and micro-SZVI. We also pre-placed those Aquifer matrix ISMs within the performance monitoring wells. Here are the plume-wide average results for 3 months and 9 months post-treatment. 3 months after treatment, the equivalent of 285 pounds of TCE was present in the treatment zone. 9 months after treatment, there was 180 pounds left. The equivalent of 105 pounds of TCE had been destroyed over those 6 months. These early results are phenomenal. The historic performance of the decommissioned pump and treat system isn't even close to what was achieved by the in situ treatment. Although the cost comparisons for this case study wasn't included in that ebook, this project is more recent than that. The annual costs for the in situ treatment will be far, far less than the underperforming pump and treat system. And the mass removal isn't even comparable with the uptime that that pump and treat system had. So this site also shows the cost and performance, the value of the in situ alternative over the pump and treat alternative. So with that, I think we can hit a couple of conclusions. And Maureen, want to kick us off?
Sure. I think, again, just, reiterating some of the comments I had made before, that when working with, plume stop and some of the associated reagents, we can create, a barrier or treatment system that lasts a long time, can be fast. Now we know the types of mass removals we can achieve. And, ultimately we're looking at an effective technology at much lower costs.
Yeah, the in situ remediation, can be much more cost effective than pump and treat. The 10-year discounted capital O&M costs for several of the sites, we calculate for both the in situ technology and pump and treat scenarios, and in both of those, the pump and treat were the one for the Arkansas site. It was generally comparable. So the rates that you can expect from a properly designed pump and treat system might be fairly equivalent to the in situ remedy rates of mass removal, at least initially over that first year. But the operation and maintenance costs of in situ remedies are much less than those for pump and treat. So the in situ remedies provide huge savings and value over pump and treat systems. And mass removal, it can be estimated for both pump and treat and in situ treatment scenarios. In those confounding factors where partitioning and low recovery, the partitioning caused by the activated carbon and low product recovery caused by these different there's beta elimination pathways that don't yield like compounds like ethene, or at least not as much. You can get over those. So the utilities of doing these aquifer volume or based mass removal estimates is really great, and those constraints are easy to overcome. So comparative mass removal assessments have shown that at these subject sites, the mass removal associated with the in situ remediation is equivalent to or better than that of pump and treat, at least over the periods that we looked at. And I actually expect that the efficiency will continue because pump and treat is going to tail off a little bit as they start reaching asymptotic levels, whereas the in-situ has a better ability to penetrate and diffuse into matrices that are a little bit tougher to deliver to initially, and you can get degradation actively happening there as well. So with that, I think we might have a little bit of time for questions.
All right, thank you very much, Matt. That does conclude the formal section of our presentation. So at this point, we'd like to shift into the Q&A portion of the webcast. Before we do this, just a couple of quick reminders. First, you'll receive a follow-up email with a brief survey. We really appreciate your feedback, so please take a minute to let us know how we did. And also, after the webinar, you'll receive a link to the recording as soon as it's available. All right, so let's circle back to the questions. We have a lot of questions, so if we do run out of time before we get to your question, we'll make an effort to follow up with you after the webinar. All right, so here's the first question. It is, what about estimating petroleum mass removal?
Yeah, it's a good question. Sorry I didn't touch on that, but petroleum and most contaminants, the method of quantifying temporal contaminant mass per saturated soil volume will work. So go ahead and do it that way. So you take a look at do that conversion where you take the aqueous samples and the soil samples, mathematically combine them into saturated soil, and do the mass assessment with time based upon those. There are also some CO2 and methane mass flux methods out there, but keeping it simple, mass per saturated soil works and works well.
Okay, thanks, Matt. So next question is, can the ISMs be used where the activated carbon is not delivered as a hydrocolloid?
Yeah, so that's the, so I think this one gets back to like if you don't have that steric stabilization like the plume stop has on it, and that makes the plume stop almost act like a soluble component, not like a colloidal compound, right, that settles out and has distribution issues. Yeah, so I think that in native aquifer material ISMs can also provide some value here. But they might not necessarily be, with these non-hydrocolloid activated carbons, they might not be delivered as efficiently. So in order to, I guess it's not stack the deck, but to make sure that you have a decent assessment of what's going on in situ, and you can't count on the ISM being dosed the same way it would be if it were hydrocolloids that were being applied. You might need to pre-mix in the design dose of the activated carbon into the ISM matrix, that native matrix, then deploy it, and then you can pull it with time and see, am I getting degradation? Is the mass of sorbed material decreasing? And it would at least give you a signal that it was time to go out and collect an actual saturated soil sample.
All right. Okay, thanks, Matt. So here's another question. It is both in-situ treatment and pump and treat have been around for a while. Has in-situ always been as efficient with mass removal as pump and treat?
That's a great question. So I think there's two components to this. So first of all, recently, over the past 10 years for sure, but even more like over the past 5 years, we've learned so much about degradation pathways, and that they're not as simple as kind of what I showed today's example, that a lot of things go into them, and that you need to pay attention to all those inputs to make sure you've designed well. So I think because those pathways have been detailed much more significantly recently, it allows design engineers to provide exactly the conditions that are needed to stimulate degradation. But I also think there's a component, the second part of this, is that remedial amendments have improved. And Maureen, can you comment on how remedial amendments have changed over the past few years, to accommodate this new science?
Yeah, Matt. No, I'm happy to. In thinking about, ERD reagents, we can apply that and you get some removal. But I think the advancements, particularly with colloidal carbon, um, gives you some more predictability. It also increases longevity. And so I think those components make it really important, particularly if you're thinking about a barrier and being able to maintain that over long term. And I think then the other aspect is rebound. You may get low levels, or maybe you're using ERD, it goes down and comes back up again, and you get this rebound. And being able to manage that rebound, that's something else when you're working with some of the colloidal carbons. I think that's really advantageous and something that's newer and gives us more tools and better tools for the in-situ.
Okay, thanks, Matt and Maureen. So here's another question. It is regarding the Arkansas site. It says you completed 2 pilot tests. Why did you go with plume stop over biogeochemical?
Good question. The biogeochemical worked well, and so did the plume stop. But we saw the biogeochemical as being additive to the plume stop. So, and we actually had a decent background of sulfate and iron, and the missing material was a fermentable donor, which we were adding to stimulate the biodegradation as well. So I think we did get some biogeochemical conditions formed with our application. Good question. They both performed well, but we thought that we could get a biogeochemical component included with the plume stop as well.
Okay, thanks, Matt. So here's another question. It is how are bioremediation and iron-based abiotic pathways complementary?
I know Maureen's all over this. We were talking
Yeah,
about
if you want, I'll jump on this one. Matt actually had touched on some of this, so I think a little earlier in his presentation talking about, how you utilize both components. And I think they really are complementary. I think in some aspects, number one, the iron, that can help you really create those conditions immediately, those reducing conditions, and can have some very fast rates, particularly with the parent compounds. And then the bio just really supports this and may have some better efficiencies, maybe even with some of the vinyl and other daughter products, or even some other compounds where ZVI isn't necessarily as as effective as bio is. So the two really work well together. And honestly, we've internally at REGENESIS done a deep dive on some of our in-situ programs, with and without iron, and we certainly have seen a statistically significant, impact on the data that by adding the iron, that we're getting better overall results, both in rate and, percent reduction.
Yeah, and I think that some of those, those synergies, show up if you take a detailed look at each of the degradation path or each of those, pathways. For example, dihalococoides, the main actor in sequential degradation of chlorinated solvents. It requires B12. It can't make B12 itself, just like people can't make B12. They've got to take, we've got to take some vitamins if we want to get B12, or have rich diets that are rich in B12. Dihalococoides are kind of out there on their own because they don't have access to these vitamins, but other microbes produce it, and then they're able to grab access to it. But in one of the groups of microbes that can make the B12 are iron reducers. So when you're adding iron to a system, and you get Geobacter growing up that makes B12, and it's probably even the right lower ligand. And for the only there's 4 lower ligands of B12, and DHC uses one of them. So just having a diverse population of microbes making all sorts of different variants of the B12, things like that, the details of those degradation pathways probably leads to a lot of those synergies that you're seeing empirically.
All right, thank you, Matt and Maureen. So that is going to be the end of our webinar today. If we did not get to your question, someone will make an effort to follow up with you. If you'd like more information about engineering solutions from WSP, please visit WSP.com. And if you'd like to learn more about remediation solutions from REGENESIS, please visit regenesis.com. Thanks again very much to Matt Burns and Maureen Dooley, and thanks to everyone who could join us. Have a great day.